I'm going to get started. The aims of today's session, I would like you to become familiar with the fundamentals of teaching for mastery and what that means. We're going to talk a lot about the importance of CPA. If you don't know what that stands for, don't worry, I'll be going through it all. And then I really want to introduce the 5 big ideas of teaching for mastery. And so the bulk of the session is going to be around that, the 5 big ideas of teaching for mastery. I'm going to be going through each of them very briefly at first, and then we're going to be going into each one of them in more detail. And hopefully we'll have a bit of interactivity, and I'll get you guys to be answering some questions as well. So first of all, I always start with this in my math training sessions because I think it's vital for us to understand what it is we're working towards as teaching practitioners in our maths lessons. So the 3 aims of the national curriculum. The first one, becoming fluent in the fundamentals of mathematics. So people often think of that as learning your times tables, knowing your number bonds, and it states frequent and varied practice and then rapid recall. The second aim of the national curriculum is reasoning mathematically. So this is really heavily focused on mathematical language, correct mathematical language, following a line of inquiry, conjecturing, lots of really nice example of reasoning questions from White Rose. If you've heard of that maths organisation, they have an absolute ton of really rich reasoning questions, which I do recommend you have a look at. And then the last one, which I think is the most important one, and it's what we're really here for as math educators, is solving problems, because that's essentially what children are going to be doing when they leave our classrooms and in the wider world when they're older. Solving problems in routine and non-routine contexts. So contexts they're familiar with, contexts that they are unfamiliar with. Breaking down problems, knowing how to seek solutions, having that perseverance. So 3 main aims, essentially fluency first of all, reasoning and problem solving. So that's just to sort of set the scene for what we are working towards. Now, I'm sure you've heard of the word mastery in lots of different contexts, hopefully related to maths. And I thought it would be useful just to start off by clarifying what it's not. So mastery is not some special higher level of attainment that some children will get to and some won't. It is very much all these things. It's a belief that all children can succeed at maths. So this idea of a growth mindset, you can't do something yet. It spends longer on the big ideas, so the fundamentals. I'm talking number formation, one-to-one correspondence, place value, all of those absolutely essential ideas that children need in order to be successful mathematically. It doesn't like to be teaching them superficially and then moving on. It really wants to embed these key ideas. And I'll be giving an example of that later on. In an ideal teaching for mastery scenario, you would have all the children moving together through content. Now, I realise that is tricky in practice, but what that means is that you're not exposing some children to different contents because they've grasped an idea. So you're not accelerating them. You don't have traditional differentiation in the sense of you have 3 different worksheets, for example. Everyone is exposed to the same content, but it might be that those who have grasped something quickly are stretched through depth of understanding. Those who are struggling with the concept have more support in order to access it. And what it's trying to do overall is ensuring deep understanding before moving on. And it really focuses on that mathematical understanding. It really focuses on mathematical relationships. So for example, it is not just a case of great children can add 1-digit numbers quickly in their head, we'll move on. It's looking at all of the patterns, all of the relationships within that, all of the different conjectures they can make, all of the problem solving within that. So why are we teaching with mastery? So it's a bit of a sort of national phenomenon at the moment. The organisation, the NCETM, are really pushing this throughout the country for many, many reasons. They want to provide the highest quality mathematical education for our children, prepare them for a mathematical future. And really it's about this, to avoid this big gap from forming between classes. To try and avoid, where possible, inheriting a cohort of children where you have the majority of children sort of in the middle, and you have some that are sort of high flyers and they're off doing much harder problems, and then you've got this cohort that maybe were in the low group, if that was a term that was used before, and they never move out of that low group. They are just always in the low group. They have very few opportunities to move out of that group. It really wants to avoid that. And it's come very much from Singapore and Shanghai and those East Asian countries, this idea of teaching for mastery. I've just flagged up here, and I'm going to put it in the chat, this summary page, which hopefully goes through everything I've just talked about, but with a little bit more clarity. And I'm just going to pop it into the chat so that you can reference it at a later point, or if you're working with staff members who are asking you what mastery is and want a little bit more clarity or somewhere to go to, you can sort of have this summary. So I'm just going to pop that in there. Hopefully you can all see that and access it. Now, I had the absolute privilege of going to Singapore a couple of years ago and seeing the maths teaching in action. I've also been very privileged in being able to work with Shanghai teachers on a number of occasions when they've come to the UK to do some sort of model maths teaching. And what I will say is that this idea of teaching for mastery for them is just maths. They know no other way of teaching. This is just how they teach. They teach for understanding and they teach for depth. So I'm hoping throughout this training I'm going to be including lots of elements of that and of my experience of what teaching for mastery looks like in the country that I've seen, and in the colleagues that I've had the benefit of working with. Summed up, what teaching for mastery is not, and this is what I thought before I knew anything about teaching for mastery, before I went to Singapore. I thought, so I know they have large classes, but it's really passive learning because they just do lots and lots of rote drilling and lots of chanting, and that's how they learn maths. But I could not have been more wrong. They are very much active learners. They're taught to think mathematically, and what we might have termed rote drilling, they call intelligent practice. It could be linked to variation as well, which is linked to fluency. I'm going to talk about those ideas a lot more when I'm talking about the 5 key ideas. So what is the research behind mastery? What is the research that has gone into this? Now, I'm sure you can appreciate that there's a lot. And so I'm just going to give you a flavour now of the different elements that are behind teaching for mastery, and I really hope that some of this is familiar to you and you will recognise it from your own teaching practice. So the CPA approach, which stands for Concrete, Pictorial, Abstract, was really advocated by Brunner as having something physical for children to pin their ideas onto. I am sure you have all heard of Vygotsky, and he was a huge advocate for the rich discussion and peer talk, which is very much a strand through the mathematical reasoning element of teaching for mastery. Again, I'm sure you've heard of Piaget. He and his research was very much around thinking processes rather than outcomes. So the answer only being the beginning, and tackling and unpicking how we got to that and the multiple ways of getting there. And at Liu Academy Trust, we very much follow the Mass No Problem scheme, and the structure of the in-focus task, it is exactly the essence of that. It's the process of having got to the answer rather than this is the answer, we'll move on. So somebody called Stemp talked a lot about instrumental understanding. So you can think of that like rote rules, and relational understanding. That's understanding what and why. Now, mastery teaching very much focuses on what and why. Of course, you need to have your rote rules. You need to know your times tables. There's no sort of debate around that. But where previously maybe traditional teaching would have left it there, a huge feature of mastery teaching is understanding why, being able to explain, spotting when a problem has gone wrong, and then running with different patterns and conjectures. And then Dean, I am sure you've heard of Deans. So somebody called Zoltan Deans was a huge advocate for exploration before structure. So I'm sure, hopefully, you all have deans in your classroom, or you all have heard of deans at the very least, or base 10, if you might call them. And that is just one of many different ways of this physical structure and exploring the structure of mathematics concretely. So very much linked to what Bruno was saying. So I'm hoping that none of this is new to any of you, that, using resources is a feature of every lesson. There's lots of rich talk and there's lots of discussion over why something is, as well as just the fact that it is. Now, to give you a really quick pause from hearing my voice, I'm going to show you a quick video from Debbie Morgan, who is the head of the NCETM. And this is just going to very briefly, and I'll pop the link in the chat if you want to refer to it later, briefly going through what teaching for mastery is, what the different elements of it are. It's about 3-4 minutes. So I'm just going to play that now. If you can't hear it, or if there's a problem, just pop it in the chat and I will I'll try to remedy that.
As a country, we're very inclusive, and we need to be proud of that in terms of our education system. But I think what a mastery curriculum is making us think about is how maybe we need to implement inclusion in a different way. The key principle of mastery for me is high expectations that all pupils will achieve, and the mastery curriculum, its principles, its characteristics support us in doing so. And I think teachers are beginning to understand that and beginning to see a way forward in making a difference for teaching and learning, in particular deep and sustainable learning for their pupils. I think one of the big issues is differentiation. Teachers are very used to differentiation. It's become part of their practice. They automatically think, I'm going to have at least 3 different groups to teach in my class. And in a sense, differentiation seems to make sense. It seems to make sense. We've got some children who could accelerate and go quicker. We've got some who need to go slower. But what we need to think about is that those who are in the slower track, we do it to catch them up, but they will never catch up at that rate. And so I think one of the challenges is how you teach a whole class but still meet the needs of all pupils. And there are ways to do that. The key way is in terms of the teaching for depth, so that you're not accelerating anybody, but some children are thinking more deeply than others. But everybody's thinking deeply, everybody's going more slowly, so they've got opportunities to think deeply and really embed key concepts. So differentiation, I think, is a key challenge. I think assessment is a key challenge. The reason assessment is a key challenge is that a mastery curriculum requires a completely different way of thinking about assessment. The system of levels which we previously been working towards and teachers were held accountable for, was that we would accelerate pupils into the next level as quick as they could. The result of that has been rapid over progression with superficial learning and insufficient depth, so that the teacher who teaches a topic 1 week comes back to it 6 weeks later and she feels like she's starting again. There's been not very little has been sustained over that time, and for some children nothing's been sustained. She's starting again. So I think in terms of then of assessing that, if all the class are working together at broadly the same pace, some children will make greater progress, but what does that look like? I believe that looks like that they're thinking more deeply about the same content on the mathematics. So in terms of assessment, we need to have systems that assess for depth and not assess for acceleration in terms of content.
So that was just a sort of hopefully a summary of what I've gone through. The thing that I thought was really key that Debbie Morgan touches on is this idea of you've taught something to your children and then you come back to it half term or a term later, and it's like you have never taught them anything. And that sense of always having to start again. And that is exactly, in a nutshell, if you like, what Teaching for Mastery is trying to avoid and is trying to stop. So I'm going to talk about CPA now, which I'm hopefully you're all familiar with. So I'm going to go through each of the stages, and then I'm going to go through or show you what this might look like at different key stages, because it's vitally important that it is not just concrete resources are in key stage 1 and then never come up in key stage 2. So the concrete stage of lessons of understanding, it's very much the doing stage. So it's not just a case of the teacher shows someone how to work something out and then they go and do it, but it's about that experience of handling those concrete objects. So important lower down the school, Key Stage 1, where they're grappling with number, but equally as important going into Key Stage 2. And this is often the stage that I feel gets lost in Key Stage 2, and resources don't come out because teachers think they don't need them or they understand. It is as important in Key Stage 2 as it is in Key Stage 1. If you think about every maths concept you're teaching will start off as abstract. So we always get physical resources out when we're teaching children to count or to assign numbers to objects. That's pretty much standard. I don't really think I've ever seen a teacher who doesn't do that. But fast forward a few years, you're teaching fractions, you're teaching algebra, you're teaching negative numbers. And often no resources come out. But if we think about that, how is learning about that abstract concept any different from when they started learning about number? The resources should be used in exactly the same way as when you're introducing number to the younger children. The pictorial stage, you can think of it as the seeing stage or the drawing stage. And it's a really fundamental step. It's visual representations of the concrete objects. At Leo Academy Trust, we have journals or journaling or maths books or whatever you want to call it. And that representation of what children are thinking is crucial. It starts off in Key Stage 1 very much drawing the physical objects, like drawing cubes or drawing, Deans, for example. Again, it is vitally important in Key Stage 2. I'm going to talk about bar modelling a lot later, but one example of the pictorial representation in Key Stage 2 is the use of bar modelling to represent problems, to represent equations. That drawing of a problem, as important later on as it is when you first introduce it. Essentially, it's helping children internalize those concrete structures and then almost visualize them on paper or in a way that they have drawn or that they have made. Very, very important for problem solving. And that's throughout all the year groups, that pictorial representation of what it is you are having to do. The abstract stage, I'm sure I don't have to explain what that is. It's the symbolic stage, so the numerals or the equation notations, all the different symbols that come up later on, like squared, the division symbol, all of that essentially. So I often find that teachers focus very heavily on this abstract stage of learning. At every key stage, because it's on the worksheets, because they need to know number, and yes, of course they need to know number, but the CPA approach I have found is the most successful when you're using the concrete and the pictorial alongside the abstract, and they're not being used as separate entities, and then you always introduced abstract concepts through the use of concrete and pictorial resources. So here's an example of what CPA might look like in Key Stage 1. They often find that Key Stage 1 is the concrete resources and pictorial representations. Not really a problem in Key Stage 1. Teachers often have them, they get them out. There's lots of physical resources, lots of counting, lots of teddies and buttons and all sorts of things. Here's an example. You might have a word problem that's related to apples. So you'd have real life apples. You then might represent the real life apples with cubes or with counters. The pictorial stage would be, for example, drawing those apples or drawing that bar model where each square represents an apple. And then obviously the abstract notation where you're adding them together at the end. So this is an example, and this is from one lesson in Maths No Problem of the CPA approach. And I stress that this is from one lesson in Maths No Problem. It is not on one day we have the concrete, on one day we have the pictorial, and one day we have the abstract. It's all together, it's all introduced in a very controlled manner, but all alongside each other. So the concrete and the pictorial is supporting the understanding of the abstract. Here's an example of what it might look like in lower key stage 2. So this is, I think it's a year 3 example from Masto problem, if you're familiar with it. It's a multiplication problem, or you can see it as a repeated addition problem. In the problem, we've got donuts, and if you're lucky enough to have all these real donuts in real life, that's great. If not, we've got the picture of donuts. That has then been represented with deans, and then we've got the abstract scaffold, if you like. So not just the sort of bare equation, but this scaffold is something that's been made in order to support the understanding of the concrete resources. And by that, I hope that wasn't too woolly, just to explain, this example, the tens column has been color coordinated to match the tens. Deans, the ones has been color coordinated to match the ones. You've got the picture of the concrete resources next to where they're having to write how many ones there are and how many tens there are. So that's an example in lower key stage 2. Here's another example in lower key stage 2. This is actual photos of deans and place value counters. Very similar way. Children make the equation. They've got a drawing of an equation in order to support the abstract understanding of the equation. Here's an example from upper key stage 2. I hope it's not too blurry. I really tried to zoom in on this. So this is comparing fractions. This is a year 6 lesson. And as I've hopefully stressed throughout, the concrete resources are as vital and as important in upper key stage 2. So here we've got some Cuisenaire rods to help children compare fractions. You've got the concrete Cuisenaire rods as your concrete resource. The pictorial is where the children have drawn them out and drawn them as a bar model. And then the abstract notation underneath is where they're actually comparing. So this was an example from year 6 of CPA in one lesson. Here's another example of concrete pictorial abstract. So the cubes, sometimes you don't see them in year 6, but they can be just as valuable. This is a year 5 lesson on the left, using the multi-link to explain why those are prime numbers, using place value counters to explain that horrible long division, which I know lots of teachers hate, but what a much clearer and more visual way of explaining these abstract concepts. So I hope if you are in upper key stage 2, in the last, 5 minutes or so, I have stressed the importance of concrete resources in order to help your teaching of these higher order thinking questions. So now I'm moving on to the bulk of my session, which is going to be about the 5 big ideas of teaching for mastery. Now, this document is from the NCETM. It really is going to be a whistle-stop tour because I spent 2 years training with them to become a mastery specialist. So I've really condensed it all down. But what I'm hoping I'm going to do is give you a flavour with examples of each of these elements, what it means, what it might look like in your lessons, and hopefully what it means for your practice as teachers in your maths lessons. So representation and structure. So that's a lot of pattern seeking, making connections. I'm going to talk a lot about the key representations that we should be introducing to children. We've got mathematical thinking, which is a lot about chains of reasoning and making connections, which you'll notice again comes up. The fluency, so the number facts we need, the table facts we need, and again, you'll notice the making connections. Variation, there are 2 types of variation, which I will go over. There's procedural variation and conceptual variation, and again, making connections. And then this idea of coherence, which runs through all of these 4 ideas. And the big idea of coherence is that small steps are easier to take. So that, if you haven't seen it before, hopefully you have. If not, this is what the snapshot of teaching for mastery looks like, and what all teaching for mastery schemes are based on. What I'm going to do now is I'm going to go through each of these 5 ideas in a lot more detail, and with some examples as well. I should probably say at this point, does anyone have any questions or anything? I mean, I'll keep going if not, but please feel free to let me know any questions that you have. So the first one I'm going to talk about is coherence. So this is coherence sort of summed up. It's small steps that you take, focusing on one key point, thinking about progression, and then mastery leading to application. Now, that all might sound a bit wordy and maybe you're not quite taking it in. So I'm going to go through an example to help you as teachers understand coherence and put you in the position of maybe what it's like to be in a class and have a maths problem in front of you. So if you were in a room with me, which I know you're not, so you're going to have to sort of imagine, I would say to you guys, can you read this to me? Read this out loud. And I won't get you to unmute and tell me, but I'm guessing that you would struggle to do this because you're not familiar with the symbolic notation. You don't know which way you're reading, and you don't know what sounds the symbols make. And if you're thinking about a child who has difficulty with whatever it is, number recognition maybe they don't understand the greater than, less than signs, maybe the fraction line in a fraction, they don't really know what that means. This is what it's like for children when we are giving them maths that is, far beyond their grasp, or we haven't scaffolded enough. This is what it feels like for them. They don't have anything to pin their mathematical ideas onto. There's nothing for them to progress from. So what do we need to do? We need to break it down into something that is more manageable, accessible for them, in order for them to, not giving them the answer, but into leading them to be more successful. So here I have got written how you would read this word out. Now, I confess I do not know how to correctly pronounce this word, but I could give it a go because I now recognize the letters, I recognize the symbols, I can see there's spaces between some of the letters, so I know that I say them separately. I've got a much greater chance now of accessing this mathematics because of the step back that I've taken as a teacher in order to scaffold it and the support that's been put in. And so this idea of coherence is when a new concept is encountered, in order for the child to be able to learn, one of two things must happen. Either the new idea is connected to and incorporated into the learner's existing framework of knowledge, so that's assimilation, or the existing knowledge structures must be extended or reorganized, and that's called accommodation. Maybe if you studied education at uni or you did psychology, this idea of assimilation and accommodation might be familiar to you. But either you've got to incorporate it into what you already know, or you've got to expand what you know. And the research supporting coherence, and again, this is just like 10 seconds into what is years and years of work around this, is that mathematics is this connected body of language. And with this in mind, coherence in mathematics education involves taking learning in very small steps while making connections with previous learning so that the learning is deeply understood. So what that means for us in terms of mathematics practitioners is that it's almost like taking the long road and taking longer around understanding a concept, properly scaffolding it and supporting it in order to promote understanding. I've got a mathematics example for us now. If we were all in the room, I'd be asking you to input. So I'm sorry that I'm just keeping on talking at you, but unfortunately we're not all together, so I'm just going to keep going. If I was to ask you, how do you multiply a number by 10? And I gave you this worksheet. Now let's think about the teacher who says, you just add a 0. You could have a child or children, and I've had children, I'm sure you have if you're an experienced teacher, who could fill in this whole worksheet because they know the rule, they know the trick. You just add 0. Now, I'm sure you can already thinking all of the problems that come with that. What about when you say 10 times 10? How many zeros are you adding? What about 0.6 times 10? Do you still just add a 0 there? Does that work? What about the inverse? What about 3 divided by 10? The child that has just been taught to just add 0 might superficially look like they've grasped a concept, and they could probably do reams and reams of these worksheets. You could even teach them that to multiply by 100, you add 2 zeros. and to multiply by 1,000, you add 3 zeros. And they could produce pages and pages and pages for you with all lovely correct answers, and they're feeling proud because they've got it all right. And superficially, it looks like they've grasped that concept. And this is what Debbie Morgan was talking about, is that superficial acceleration. Can they apply it to these other scenarios? No. Do they have that deep mathematical understanding? No. So where does coherence come into it? It's breaking it down into those small steps, and it's going slower. So at the bottom there, I've got the example, as I'm sure you know you would need to do, of the explanation is that you move digits up the place value column to make them 10 times bigger. That's the first step you take. And then the next step you take might be to tell them that in order to multiply by 100, they have to move 2 times up the place value column. And then to do the inverse, they move, down the place value columns. And if you're doing 10 times 10, well, that 0 counts as a digit, so it moves, but then you put 0 in as the place value holder. That takes a lot longer. The child who gets taught like that, it may not be doing reams and reams of worksheets at first that look like this. However, you're teaching them with coherence. You are teaching them small steps in order to avoid superficial acceleration and embed mathematical understanding. So hopefully that gives you a little bit more understanding of what coherence is, and the importance of, I'll just go back to that first bit there, that small steps and only focusing on one key point at a time. So in the example I gave, the small steps of focusing on place value columns, the key point of understanding the relationship between each place value columns, relating that to what the inverse would be. And then you're thinking as the teacher about progression. You might not be teaching all of those things in one lesson, but what we need to have as teaching for mastery teachers is that knowledge of where the children are going to go. And so teaching it right, if you like, from the start in order so that children can progress and they can assimilate or accommodate the new piece of mathematical information you're giving them in order to progress, as opposed to just teaching them rules or tricks. And if we teach like that, so that last point, which hopefully makes a bit more sense now with the example, mastery leads to application. The child who has mastery embedded for multiplying by 10 will be able to apply this to multiplying by 100, multiplying 1,000, dividing by 100, divided by 1,000, etc., etc. So hopefully that's a bit clearer now as to what coherence is. So I'm just going to whiz forward. Whistle stop tour again onto representation and structure. So again, I'm going to go through these points. I'm going to give you some examples of what this looks like in lessons and what this means for us as teachers. And hopefully this will make these points I'm about to go through clearer. So the first point is that representations reveal structure. There is so much structure in mathematics, not just place value structure, but the patterns in number, in our times table system, all sorts. And so the physical representations reveal that. Representations are a very useful aid in learning, but they're not an end in itself. Manipulatives, concrete resources, if you like, are key representations. And I'm going to talk about what the key manipulatives are that we should be using in our classrooms. This idea of stem sentences describing a representation, and they can be a representation in themselves. So today I was actually teaching you that sentence of 32 has 3 10s and 2 1s. Glad I got there in the end. That sentence is a representation in itself, because if you take the numbers out, you've got has 10s and 1s, and you can put in any number into that. 17 has 1 10 and 7 1s. 78 has 7 10s and 8 1s. That stem sentence is a representation in itself of 10s and 1s. Some key representations appear time and time again. I'm sure you're going to be familiar with the ones that I mean, but I do want to show you how the representations which traditionally might have been thought of as being just in Key Stage 1, I want to show you why that is not the case, and they are equally important and valid in Key Stage 2. And that pattern and structure are related but different. So those are the sort of like bullet points. Let's go through some examples now. So the first representation I want to go through is the 10 frame, or the tens frame. So here's a tens frame. It's just been split up into 5 and 5. And if I ask a child, how many vehicles do we have? Can you put them into a tens frame? Well, what the tens frame does is it reveals the structure of that number. So tens frames can be used to prompt different mental images of numbers and different mental strategies for manipulating those numbers, all in association with the number's relationship to 10. So by putting these vehicles into a tens frame, not only can I see the pattern between, well, I can see the top rows filled up, so I have a full 5 row of taxis. I don't have a full row underneath the fire engines, so I must have less fire engines than taxis. I still have, even though I don't have 10 vehicles, there are 10 spots on my tens frame. So I can see that overall I have less vehicles than 10. So there's so many things I can come up with this, and this is very much the making connections part. What I've seen teachers do is a question like this, and they show, the 5 taxis and the 4 fire engines, great, and then they just move on. And I'm thinking, no, there's so much more you could say. Think about all of the rich depth you can pull out from this. There are more taxis than fire engines. There are less fire engines than taxis. The number of vehicles is less than 10. All the things that you can pull out of that before we even bring in numbers into it, before we even have to look at putting a 5 next to the taxis and the 4 next to the engines. It's just focusing on the relationships and making those connections. So that's just one, and it's a whistle-stop tour of tens frames. The other one, which again, I hope you're familiar with this, is the part-part-whole model. Now, if we were in a room together, which unfortunately we're not, I would be getting you to be making things on tens frames, making things on part-part-whole models, telling me the relationship between them. Again, I'm sorry that we're not able to do that, so it's just going to have to be coming from me. But the structure of a part-part-whole relationship, absolutely key. Just to briefly go through, as I'm sure you know, you have your whole that can be split into 2 separate parts. And from about year 2 onwards, they're very much used to show tens and ones in a number. Not just for that, but they are one of the most common uses. And that tens frame, we've got our 8 apples in total, and we've got 5 that are red and 5 that are green and 3 that are red. That tens frame, which most children are introduced to as one of the first representations, that lends itself beautifully into being represented on the part-part-whole model. The part-part-whole model can be both a concrete representation and an abstract, because I could put my 8 apples up there in the whole, and then I could show I've got my 5 green underneath and then my 3 red there. And then I could be writing the numbers alongside, and then eventually just having my abstract, as it is here, abstract representation with just the numbers. And I just want to show you how the part-part-whole model progresses. So I talked about using tens and ones. It's often the case with the part-part-whole model, showing it with tens and ones. Not always tens and ones, though. Really important to show those different relationships. I've put that question in there on the right for all of the upper Key Stage 2 colleagues out there who think that they don't need to worry about part-part-whole models. This is a year 6 reasoning question, I believe, from White Rose. Obviously, the bits in red were the bits that children had to fill in. And I can tell you, the children, as I'm sure you can imagine, the children who had not worked with part-part-whole models since, I don't know, EYFS, struggled so much with this question, even when they were very proficient at fluency with fractions, when they'd seen it, in abstract equations. They were multiplying fractions, they were dividing fractions, but show them this part-part-whole model, when they'd not been exposed to it before, could not see the relationship between the whole, the part, and the part. And I just think that's absolutely fascinating. So Key Stage 2 colleagues out there, I hope in the 2 minutes that I've had to talk about part-part-whole models, I have proved to you the importance of still using these representations. Bar modelling, and I've actually got a link here because I'm going to so briefly show you bar modelling, but I am running more training on this on Wednesday, the 21st of October. I am actually going to pop in the form for this into the chat now if this is whetting your appetite enough that you want to find some more about it, because I'm not going to be spending long talking about it. Here is just one slide showing one bar model and all the different ways you can use it. So all the way from 4 add 4 add 4 in Key Stage 1. And if you just cast your eye all along it, look at the progression, look at what we end in, divide 12 into the ratio of 2 to 1 or 2/3 of 12. It is the same bar model. And when I was in Singapore, bar models were used for everything, at every age. Children that were younger were making them with cubes all the way up to Key Stage 2, where they were drawing them out like this. And I just wanted to show you this slide because I'm so conscious I have so little time, but just to prove to you the power of a bar model. If you want to find out more about bar modelling, because I've got a whole other session where I can just talk about bar models, please do sign up to that training where I'll be going through this and so much more. And again, Key Stage 2 colleagues, how can you use bar modelling for Key Stage 2? How could you use bar modelling for algebra? Well, here's an example. What are the relationships, fraction relationships or just multiplicative relationships between the Cuisenaire rods here? So here's an example, G equals 3R and T equals 4R. Now, I bet you didn't think that you could do that with Cuisenaire or bar modelling, but again, it's another way of a representation being equally as powerful in Key Stage 1 as it is in Key Stage 2. And that's all I'm going to say on bar modelling, but I hope I've whetted your appetite enough to want to come back and find out some more. Place value chart, key representation to highlight the tenness in our place value system. So these are just some brief examples, starting off with tens and ones, then obviously building up. The concrete resources we have to support that, we have got deans, or base 10 if you call them, and place value counters. I will say that deans are always to be used first to represent place value because they are proportional. So a 10 stick, if you like, is 10 times bigger than a 1. 100 is 10 times bigger than a 10, etc., etc. Whereas place value counters, they're all the same size. Now, this place value chart, or these ideas of base 10, I don't know if you can quite see in that photo, but again, so important at Key Stage 2 because that place value chart actually has what you might call the thousands block, is actually 1. And the tenths are represented by what you might call the 100 block, and the hundredths are the 10 block, and the thousandths are the 1. So that was a Year 5 lesson where I was introducing decimals with the support of my concrete resources. So that was like such a whistle-stop tour of representations and structure. And just because I'm aware we don't have much time yet left, we are going straight on to mathematical thinking. So children should not just be thinking passively, they need to be active recipients in their maths classes. They need to be looking for patterns in order to discern these structures, looking for relationships and connecting ideas, and then reasoning with it. I've got, again, an example which I hope illustrates this much clearer for you at home or at school or wherever you are. Have a look at the 5 times table. Have a look at set A, have a look at set B. Exactly the same questions in set A, exactly the same questions in set B. Now, if we're in a room together, I'd be able to heckle you guys and ask you questions. I can't do that. So what I would be asking you is, which set do you think is going to lead to mathematical thinking? Which set do you think is going to lead to making connections or making generalizations? And what I hope you would say is that set B draws attention to the relationship, in this case, of 5 times an odd number, ending in 5, versus 5 times an even number, ending in 0. Now, what I want you to notice is that, well, I'll go back one, the questions are not different. They're exactly the same. But I very carefully, or I've thought about how I want to order them and how I want to present them to the class, because the aim of this particular exercise is not just to learn your 5 times table. And children that know their 5 times table, does that mean they start to learn the next one? No, it means they look for patterns within the 5 times table, because fast forward to this Key Stage 2 question and think about how set B, or the way it's been represented, might help with this question. I'm just going to give you 2 minutes to read it to yourself and think about what the children need to know in order to do this question successfully. I'll just give you 2 minutes. So hopefully you've had a chance to read that question and work out that when you've represented the 5 times table in the sense of set B, when you've had those deep mathematical conversations and made connections even with a numicon, with 100 square, about odd and even numbers times 5, come to this reasoning question, which I think it's year 5, 6 from White Rose as an example. And the child that has those connections and has been taught to think mathematically like that will know that if the answer has to end in 5, it has to be multiplied by an odd number. And instead of going through the process of elimination and working out all the infinite possibilities that question would give you, it literally reduces the amount of cognitive load by so much. So ironically, the child who's been taught to think mathematically actually has to do less maths. They have to do far less 3-digit times 2-digit. They don't even have to work it out because they know a number ending in 5 times an odd number will end in 5. Therefore, and they can work out what the possible combinations are. So again, that's an example of it's not necessarily reinventing the wheel, but it's just when you're teaching something and you think about in terms of fluency, which I'm literally about to go to, how are you teaching it? What are you drawing their attention to? So straight on to fluency. Fluency is more than just memorization or parroting facts. We don't want fact fluency to hinder problem solving. We don't want children who are working out a problem that needs times tables to be sitting there working it out, and it hinders their problem solving because they just don't have those facts. However, fluency, it demands flexibility. Let me show you what I mean, and let me show you what I mean in terms of going back to that coherence and mathematical thinking. This is an addition chart. I believe it's from the NCTM. These are all the number facts from 10 add 10. So yes, children have to know them. I don't argue with that. Of course, they have to know 10 all the way up to 10 add 10. But look at the way that it's been color coordinated and color coded in order to reveal so many different patterns that are within that. And look at the organization, look at the structure. The child who is taught to do 1-digit, add 1-digit up to 10 in this way and being taught in this order and exposed to these ideas is going to have so much more flexibility in terms of bridging over 10 or spotting near doubles or knowing their number bonds to 10 or compensating and all of those kinds of things. Similarly, this is a subtraction chart. I actually made this when I was working with year 1 and 2 last year because I had some children saying, or parents even saying, oh, these are so easy. They know these questions. We don't need to keep on doing it. It's boring. And I just highlighted just the one row of number bonds to 10. And then I said to the children, it wasn't coloured in orange, can you colour in all of the facts where you have to bridge under 10? It's just a different way of looking at these fluency facts, a different way of embedding it. And of course, times tables, which again, I will put a training link in because I could talk about learning times tables till the cows come home. I'm going to put a link in where you can join for another session on learning times tables, but just really briefly, this idea of fluency and mathematical thinking, I've actually completely blocked out 1/2 of the times table square, because if you have flexibility of working with the commutative law, you will know that you do not have to know all of the facts of your times tables. You just actually have to know half, which I'm sure you know. So if you want to find out more about fluency with times tables and everything I've talked about, because I don't have time now, please sign up to that CPD session on the 12th of November. I've put the link in the chat. And finally, this is you might be pleased to hear, the final big idea for teaching for mastery is variation. Now, I love this so much that I did my NCETM PD project on it. I wrote 20,000 words on procedural variation. It's a thrilling read if you ever want it, but I think variation is key, because variation highlights the essential features of a concept or an idea through varying the non-essential features. So you have what the concept is and what it is not. It very much links to intelligent practice, and this is key variation is not the same as variety. And I'm hoping to demonstrate to you and prove to you what I mean by that. Variety would be sort of just wacky loads of different questions. Variation is where you've thought very carefully about the sequencing and the order of questioning in order to expose a mathematical concept. And this is, to sort of sum up 2 years of my life, a little quote from research that the central idea of teaching with variation is to highlight the essential features of a concept through varying the non-essential features. Now, I realise that might be a bit woolly and hard to understand, so I'm going to go through a non-maths example first before going through a maths example. And apologies, because it is just going to be me talking at you and I can't get, it's going to be hard to get a bit of participant feedback. So this is my non-maths example of variation. I'm showing you this picture and I'm going to say, what is an elephant? Give me a feature of an elephant. And I'm going to imagine that somebody has said they have really big ears. An elephant has big ears. Right. I'm then going to show you a picture of an elephant with really small ears and say, well, what's an elephant? And so you're going to look at them both and say to me, maybe, oh, an elephant is really big. So I'm going to show you an elephant that is small. And I'm going to say to you again, what is an elephant? And you might look at all those photos and you might say, an elephant is always grey. So I'm going to show you a photo of an elephant. I'm hoping you're getting the idea of this. That is not grey. Good old Elmer the elephant. And I'm going to say to you now, what is an elephant? And you might come up with all sorts of different, categories for what an elephant is. And then I'm going to show you this. And I want you to tell me, is that an elephant? But specifically, why is it not an elephant? Because, well, let's go through, it's grey, it's big. So what I'm trying to do is show you what variation is. You vary what something is, show them what it is not, in order to promote that understanding. So let me show you a maths example now. What is 1/4? So I've got all these examples of 1/4 on a square. Are they all 1/4? So if you're in my class, we'd be going through this. Are they all 1/4? Well, what is a quarter? How do you know? And what I'm hoping we'd come up with is that a quarter is something divided into 4 equal parts. And I'd say, well, is that the same as a rectangle? Is the same true? Are these still showing me a quarter? And we'd obviously be having a discussion about that last rectangle there, really big misconception that that is showing a quarter. And obviously I'm sure you can already think of so many different ways you can show 1/4. You could do it with a quarter of pizza, a quarter of cake, a quarter of a rope, a quarter of a cup of tea. I'm sure you get the idea, anything, not just numerically. So fractions, I find, is a really easy way of explaining variation within maths. But now I want to show you an example of variation with number. This is an excerpt from a Shanghai textbook. I'm just going to give you 30 seconds to look at these questions and see what you spot. Now, hopefully, sorry if that wasn't quite 30 seconds, you will spot that there is variation within the questions and between the questions. So the first example I can see is that the numbers that you are adding or subtracting to always differ by 100. I'm noticing, I'm sorry you haven't had much time to look at this, some of the numbers you have to bridge over 10, some of them bridge under 10, but essentially everything each time is slightly different, but there is a pattern still within all of them. And this is a classic example of procedural variation. And the Shanghai textbooks are really clever in this way because they've all been designed with this in mind. And now hopefully that makes sense in terms of variation, not variety. It's not that there's just a bunch of addition and subtraction questions on that page. It's been thought about and varied very cleverly. And I'm going to be running more training on this, on procedural variation. It's going to be a training course run through the NCETM. I don't actually have the details of it yet because it's all still up and running, but it's going to be a training course very much looking at this, looking at variation within maths, within number, throughout all the year groups. So I'll be sending out more details if you would like to join that. We're going to be designing questions, pulling questions apart, all sorts of things. So this is the big ideas summary, which I'm going to have to just post into the chat. But if you want a go-to for what the 5 big ideas of mastery are, I'll send you this sort of page, which sums up very briefly what each of them are as like a quick reference, because I thought you might need that afterwards. I'm just going to pop into the chat now the link to this website. I'll just show you. So a video overview on teaching for mastery at primary, because we pretty much have run out of time now, but I want to, if you're interested, or if you want to still find out, I want you to have tools in order to be able to do that. I also want to bring your attention to this website, the NCETM Mastery Materials. Everything I've talked about and examples for your year group and your exactly what you're teaching can be found here. Primary Mastery Professional Development, Primary Assessment Materials, and Primary Calculation Guidance. So I'm going to put the link to that so you can share with your staff, you can have a look through yourself, whatever it is. So I'm going to pop that into the chat there. And then finally, I just have time, very sadly, to sum up. So my summary is CPA, crucial. The 5 big ideas, if you're in the room with me, I'd be quizzing on them, but I won't. Coherence, structural representation, mathematical thinking, variation, my favorite, and fluency. I've given you links to all the teaching for mastery materials from the NCETM for you to go and share with the staff or have a look at in your own time. And I just want to make it really clear what I haven't covered, just because of time. I haven't covered depth, differentiation, and assessment, all the fun ones. I think due to popular demand, I think I will be running those as sessions because I had so many questions about it.